Good morning, everyone. Before we started the presentation, I'd like to introduce our company briefly. Our company was established in 1991 in Omsk, Russia. And since the first day in business, we developed diagnostics system with artificial intelligence for petroleum refining and 11 other industries. In 1994, we developed the first national standard in the field of health monitoring, which recommended particular thresholds for vibration displacement, velocity, and acceleration, and rates of change over time for majority and centrifugal machines. Later, we have developed 5 another national standards in this field, including ones for reciprocating machines. Nowadays, over 25,000 of machines, over 2,400 kinds, are monitored by the compact system around the globe. In 2016, we have moved the headquarters in Houston, Texas, to deliver our experience in the US and globally. I have 29 years of experience working with this company. In 2007, I've got PhD in reliability management in petroleum refining using a real-time health monitoring system. Now, I'm the president and CEO of Dynamics Scientific. So let's start the presentation. There are 3 topics that I'd like to dedicate your time to. I hope it will be useful for you. First, I'd like to introduce the definitions for digital reliability and real-time diagnostics. Then, we will explore what engineering benefits the 24/7 real-time diagnostics delivers to refiners. And finally, how our solutions and strong technology deliver additional profit to refiners. It's well known that the primary cost and losses in petroleum refinery comes from sudden failures of equipment. Distributed Control Systems, DCS, supplies comprehensive information on the process and operation modes of the equipment. However, its health during operation escapes the attention of operators who continuously change process modes while controlling the process plant. For sustainable and reliable operation, it's necessary to provide operators with timely and unbiased information on how the operation mode affects the equipment's health before its failure. It gives an opportunity not just prevent the possible issue, but also it allows people to eliminate future issue at emergent stage and to prevent not just failure, but even redundant maintenance and repair. Within the last 70 years, the conventional approach to keep reliability of machinery at certain level hasn't changed significantly. It's based on 3 primary pillars: a safety factor, which is the ratio of a machine's structural capability to actual applied load; operational discipline of personnel, which is always striving to do the right things by the right ways; and failure recognition capability, which is an ability to predict failure before it happens. At the beginning of the reliability era, the primary method for extending reliable uptime of machinery was increasing the safety factor. However, significant over-increasing of structural capability to actual applied load led to rising costs of machinery, which negatively impacted consumers' interests. So since the middle of 50s last century, several approaches to providing the reliability of machines were developed and implemented, such as preventive maintenance, proactive maintenance, reliability-centered maintenance, and others. But all of those approaches have 2 common issues. It's poor statistics for machinery lifespan and the human error. To confine the influence of those factors on reliability, since the 70s, the main focus moved to increasing the failure recognition capability. Until now, scientists, engineers, and practitioners attempt to point out an instance of a machine's failure to be able to prevent its breakdown using different instruments and methods. We could name that era analog reliability because people strive to increase the reliability of evolving every one of those pillars and making them stronger, clearer, and more precise. Digital reliability emerged at the beginning of the 90s, when PCs were used for reliability tasks for the first time. Since that time, computers play a significant role in the evolution of reliability theory and practice. because of several reasons. Compute complex functions very fast. Second, they process large amount of data. And finally, they deliver information for better decision making to different places to many people simultaneously. The shown curve represents dependency of costs and losses by fault detection. Within its lifespan, equipment undergoes 3 stages of degradation: nonlinear wear, exponential wear, and critical wear of equipment. These are divided on the curve by the red dots. Let's consider what's the difference between machinery diagnostics and early diagnostics. Diagnostics is a process of identification of malfunctions that consists of several steps. The very first and most crucial step is collecting data about machinery health, which contains the choices of data type, data source, data volume, frequency of data gathering, and tools to do that. Any mistake at this step severely affects the diagnosis, making it either wrong or late. The process of diagnostics has 2 distinct errors: an error of static recognition and an error of dynamic recognition. The error of static recognition appears when a failure cannot be detected because either the wrong non-destructive testing method is utilized or the proper entity method is used in the wrong way. The error of dynamic recognition appears when a failure cannot be detected or prevented because an interval of monitoring equates or exceeds an interval of defect evolution from emergence to failure. The later defect is identified, the greater the consequences and expenses are. Therefore, it's critical to identify the instant a defect begins because it's the best opportunity to intervene and prevent serious accident and possibly shutdown due to equipment failure. While diagnostics itself is a process of defect detection, early diagnostics is a process of defect preventing. Existing solutions such as protection or condition monitoring systems are focused on confining consequences, not preventing breakdowns. DCS merely shows the failure, at best correctly starting the emergency shutdown to minimize the consequences of the equipment failure. It doesn't identify the fault at an early stage of degradation and take urgent actions to eliminate it. If the protection system alarms, the breakdown happens, or almost happens. Even UAI software solutions work at the end of exponential wear stage because the AI analyzes in the same parameter that condition monitoring or protection system measures. Also, almost all condition monitoring systems require an expert to interpret. Without that interpretation, the operator cannot understand what should be done to prevent an impending failure. This is the main reason why most breakdowns and accidents happen on the night or weekend shift when the expert is not on duty on the facility. To not only prevent failure, but even repairs and maintenance, we need to identify the emergence of issues in the nonlinear wear stage. When destructive forces are just beginning to degrade the equipment, particular operators need precise, proven, and timely information about what should be done to recover equipment health. With the compact system, diagnosing the health of every piece of equipment in a facility in real time and delivering precise, timely prescription to operators 24/7, an operator doesn't need to be an expert in vibration analysis to know how and when to react. If operators identify and eliminate these destructive forces at the nonlinear wear stage, the safe and reliable operation will become a reality. It's essential that only real-time diagnostic systems, which have low errors of static and dynamic recognition of defects, and which are able to identify destructive forces influencing on emergence of defects, can shift operation reliability and maintenance efficiency tremendously towards paramount safety and uptime. The compact system monitors all types of rotating equipment, including centrifugal and piston compressors, pump, air coolers, etc. The system could be integrated with DCS, PI, and other systems over either Modbus or OPC UA interfaces. The system monitors health of every piece of equipment every 3, maybe 5 minutes, depending on quantity of equipment at the facility. Diagnostic station is located in the control room, while the SCADA type field bus gathers proper data for physics-based artificial intelligence. Thus, artificial intelligence transforms sudden defects into gradual ones and alerts personnel by prescriptions what actions need to be taken to prevent failure. Here you can see the monitor mode. This mode is most important because it displays all machinery at the unit at a glance. This is customizable to any particular facility and can be divided by sections and machines within the section. The cursor shows the section with the worst condition, which you can see on the left part of this screen, and correspondingly to the machine with the worst condition inside this section. Also, the monitor mode displays various parameters measured, which you can see in top left corner. And on the top right corner, you can see the prescriptions which the system displayed to operator staff in the control room. The different colors represents different states of health. As you understand, red represents the machine in an acceptable condition and a recommended action must be performed. If the action doesn't improve the health of the machine must be shut down for repairs or switched to standby machine. Yellow color means that the machine needing action required condition and need to be performed in order to avoid additional maintenance and shutdown in the future. Green color represents acceptable condition and indicates that machine could operate safely. So different colors, easy to understand. Different prescriptions also give you a possibility to recognize what kind of malfunctions happen and what kind of stage of degradation happen. If you can see the prescription on a red background font, it means that this is an exponential stage. But if you can see the prescription on yellow background font, it means that this is a nonlinear stage. And if you eliminate destructive forces before they damage the machine, you could prevent not just failure, even you could prevent repair and maintenance. Here, we can see a list of the various types of faults that can be automatically detected by the compact system. On the left, we have a list of the types of faults found in centrifugal machines. On the right, you can see the same issues and defects in piston compressors. The compact system incorporates physics-based AI that identifies particular signs and vibration signal which are related to particular defects and malfunctions. The physics-based AI consists of a library of rules of equipment degradation and a bunch of algorithms that could be chosen by AI in order to identify particular defects and malfunctions. Decades of scientific research are behind the components of AI. The physics-based AI is developed to recognize the wide range of defects and malfunctions in various types of equipment. The system software itself doesn't contain machine learning algorithms, but they are used widely as updates and are developed. The system has several rules of degradation which describe every defect or malfunctions as a list of parameters of the vibration signal and other signals. Every parameter has its own threshold and strong correlation with a particular specific defect. So if the system identifies the parameter in a vibration signal, the defect exists and its stage of degradation is determined. So this is a main difference between statistical-based AI and physics-based AI we do offer. The typical refinery has several units which can all be combined into CompaxNet. In CompaxNet, you can see information about every unit equipped with the system. If you move the cursor to a specific sign of the unit, and you can see the different machines which are required to be repaired or maintained. So if you double click on the system sign, you can see the monitor mode and you can receive additional information, detailed information about machinery health. But every system, this is only instrument. In order to use these instruments in most effective manner, you need to implement the technology of safe resource-saving operation and maintenance of machinery. And here on this slide, you can see the scheme of that technology. Here you can see 3 information loops for management. All of them provided by the real-time diagnostic system, which is located in the center. First information loop, dedicated to operators. So operators should play a crucial role in the reliability of facility because they are at the facility 24/7. Therefore, the system identifies malfunctions of every piece of equipment in the facility and sends precise and timely prescription to operators. Operators are the only people, as I mentioned, who could prevent degradation in emergent stage because they still in facility 24/7. This is the reason why we promote the operators-driven reliability approach. When prescriptions are received, they need to take urgent actions to improve the equipment health and reliability. They could do this by themselves. They call the maintenance department or schedule contractors. Second information loop, which you can see on the left part of the scheme, dedicated to maintenance team, of course. Maintenance team could be prepared to perform a very complex repair in very short term. They can schedule repairs according to a real condition of the equipment. But to be able to do that, they need unbiased information, which could be provided only by artificial intelligence. Humans cannot deliver unbiased information because we are influenced by numerous external factors, such as social status, income level, etc. And this is just the human nature. But in order to confine the influence on humans, we also have third information loop for management staff. Management receive unbiased information about machinery health, about operators' involvement in the reliability process, and the quality of maintenance performed. The compact system provides transparency for everyone involved in the reliability process. When people work together, they try to be better because they work in transparent environment. In terms of economic efficiency, the real value which the real-time diagnostic compact system and digital reliability approach brings to a petroleum refinery comes from several sources. First, it prevents accidents and shutdowns. According to analysis of several trustworthy sources, only in 2017, an average amount of annual refinery losses due to unscheduled shutdowns was approximately $150 million. Thus, by transforming sudden defects in machinery into gradual one, refiners could avoid most of these incidents and corresponding losses and save at least $100 million. Another source of value is extended uptime. By decreasing turnaround outage and extending average uptime from existing 91 up to technically possible 99%, an average refinery could bring roughly $100 million of additional profit. Finally, an average US refinery spends over $9 million on the maintenance annually, which could be reduced significantly as well. By totaling all these figures, the total amount of additional profit that comes from digital reliability approach based on the compact system implementation for average US refinery could reach $200 million annually. Summarizing the aforementioned information, it would be necessary to list the bullet points of digital reliability. In order to reach desirable outcomes in safety and uptime, digital reliability requires proper infrastructure for collating useful data from trustful sources using the SCADA structure. Second, it needs to have physics-based artificial intelligence, which operates by invariance to extract information on time. And finally, it requires a planned diagnostic network for simultaneous information delivery to all levels of decision-making, from operators and engineers to managers. The compact system is the only one that meets those requirements and assists refiners to make the reliability paradigm shift to implementing the technology of safe resource-saving operation and maintenance of machinery. It brings timely and objective information about machinery health, operators' involvement in reliability, and maintenance quality. Moreover, it provides financial benefits which exceed investments in this solution by at least 10 times, provides confident safety of process operations, and generates prosperity for all who are involved and surrounders. Last part of my presentation, I'd like to demonstrate how you could use digital reliability to approach paramount safety and uptime. And in order to do that, you need to go through 3 steps. First is improving existing reliability. So as you can see here, after the complex system has been installed, management, operators, and maintenance teams get on the same page. All sees the same unbiased picture of real-time health of equipment. The first 6 months operating with the complex system are most crucial for the reliability project because you can see paradigm shift on upper 2 graphs. Left chart shows the monthly quantity of repairs which were performed in repair workshops, and right is the quantity of maintenance sections which were fulfilled by operators and according to operators' orders. In the first 6 months, the maintenance department completed about 15-17 repairs a month. In the same period, the operators using the system prescriptions increased the quantity of maintenance actions from 30 to 60 per month, which, as you can see, stabilized at that level. After the maintenance activity stabilized, repairs dropped to 1 per month, significantly improving the reliability of rotating equipment in the unit. Lower left is an example of this approach. For 1 month, you can see the slow increase in the vibration parameter associated with bearing defect. The system generated an action required warrant check bearing in a race. The bearing was slowly deteriorating, and after 27 days, the pump was taken out of the service for repair. Armed with the knowledge of the actual condition of the pump, there was time to schedule the repair and switch to standby machine. Upon inspection of the pump, a crack was revealed in the inner race. Lower right shows another example. You can see here 12-hour trend of the acceleration and velocity measured on the front bearing of the pump. When the acceleration increased from 12 to 24 meters per square second, the system generates an unacceptable condition warrants. The complex system prescribes check bearing lubrication and check bearing cage. At the time of an acceptable condition ordered, the vibration velocity parameter remained acceptable for another 18 minutes. Only after 18 minutes did it rise from 2.7 to 24.7 millimeters per second. Only with these early diagnostics of the issue were the operators able to proactively switch to the standby pump and prevent an emergency shutdown. There are examples how operators can improve reliability using their own skills and their own instruments, such as operation mode, process mode, a little correction, or ordering the maintenance activities. But it was just the first step. Second step is eliminating the root causes of failures. Looking at the top left, you can see that 11 machines in a facility with around 200 machines generate 80% of maintenance order. If we could eliminate root causes of these failures, the reliability of the facility would greatly improve. On the right is an example of eliminating the root cause of an exhauster. In the before box, you can see the exhauster was operating in the action required state. The maintenance team was carrying out repairs, which you can see in points 1 to 3 and 4, using the complex system prescriptions, of course, check for imbalance and check for lossless. This maintenance section included tightening screws and aligning the exhauster. But as we can see, those repairs didn't yield the desired result, and the machine kept running in action required condition. At the point 5, they invited to subject matter expert who offered to make dynamic balance for impeller of this exhaust. And after impeller was dynamically balanced, and the health improved considerably. It's also moved to an acceptable state, and its vibration decreased significantly. The root cause of an exhaustor failure was impeller imbalance. But eliminating the root cause not only reduced the risk of unscheduled and unpredictable failures at the facility in the future, but also confirmed an upgrade to the existing maintenance procedures to include dynamic balancing into the map of the procedure. Third one step toward safety and reliability paramount is eliminating bottlenecks. So maybe it's most expensive step, but it's completely, we need to do that because when the facility was designed and constructed, there was little concern with using the best engineering solution. Most engineering companies use technical solutions that are just good enough to get the facility running. Construction companies use the cheapest acceptable materials and contractors, and owners also don't want to overpay for the best solutions. As a result, there are several bottlenecks that confine uptime of the unit. Revealing and eliminating those bottlenecks is very important because it leads to more efficient facility operation. I will present an example of how to remove bottlenecks. In the center of the slide, you see two trends of different vibration parameters for the piston compressors. The upward trend shows deterioration of the valves, and as you can see, on average, every week the compressor is facing valve issues. With the incorporation of the compact system, it became simpler to compare different parameters and figure out the root causes and bottlenecks. When the reliability team compared the trends of valve deterioration with the trends of hydraulic shocks, they figure out that there is a correlation. After each hydraulic shock, suction valves quickly deteriorated. Further investigation revealed that there was no filter before the compressor, and it was dirty gas causing hydraulic shocks and consequently valve deterioration, thus poor compressor reliability. They kept two standby reciprocating compressors to keep the facility continuously running. So it's ridiculous, but the compressors was repaired once a week until a gas filter was installed. Since the filter was installed, the issue is no longer a bottleneck for this unit. But to be honest, the reliability team was trying to convince management to fund this solution for about a year. End of my presentation, I'd like to show you a table which shows the key performance indicators that best lend themselves to evaluating the performances of the digital reliability approach based on compact system. If you look at this, we can see that best work indicators for petroleum refiners and the KPIs for one of our best customers, Omsk Oil Refinery, you could compare. The Omsk refinery has been operating with the compact system for over 26 years. You can see that for each indicator, the KPI is much better when using the compact system. I'd like to grab your attention for two of KPIs. First, reactive maintenance, and second is availability. Reactive maintenance is around 0% because if you know exactly what kind of issue a piece of equipment is having, at an early stage, you don't need to wait till the issue turns to a failure. You can proactively eliminate it at the best possible time. Not everyone achieves this, but Armatics unit at the Omsk refinery did it. They have really achieved on-demand plant maintenance. But our main proud of the unit's availability, which is over 99%. The Omsk Armatics unit operated for 3.5 years with zero downtime. This was possible not only because the compact system prescribed timely maintenance and repair actions allowing equipment to run without shutdown for the maximum amount of time, but also because the personnel is really involved in reliability and have a strong commitment to effectiveness and efficiency of operations, maintenance, and production management. In the other words, it's deeply engaged in overall productivity. And the final slide of my presentation, let me inform you about our next webinar, the real-time diagnostic compact system, which we will hold on June 11 at 10 a.m. Central Daylight Time. So you could click the link to move on the registration page, which you can find in the resource in the control panel on the bottom of the screen. So thank you very much and have a great day. Thank you.